Hi everyone. Today we're going to talk about wave optics, and we're going to start treating light as a wave. First, we're going to review some models of light and answer the question, what is it? Well, under some circumstances, light can behave like a particle and travel in straight lines. This is what we're going to talk about in chapter 18 when we discuss ray optics. However, in other circumstances, light shows the same kind of behavior as waves. And then finally, what we'll learn at the end of the course is light can actually exhibit behavior that is both wave-like and particle-like. So we're going to look at some three models of light. The wave model, which is what we're going to discuss in this chapter, basically lets us understand why we see certain colors upon reflection from objects like the wings of a hummingbird or the sky. The ray model allows us to figure out how images are formed when we look at an object in a mirror or through a lens. And finally, the photon model, which we'll get to at the end of the course when we start talking about modern physics like quantum mechanics. We can treat light as a particle and a wave. So the reason why we know that light can behave as a wave is through a very simple experiment. In this picture, we have water waves, and you can see the amplitude of the water by looking at the bright spots on this screen here. And that's the crests of the water as we're looking down. And what we see is that if we create a small opening, an opening that is roughly the same width as the wavelength, what you'll see is when we shove the water through the opening, you are going to start to see this curvature appear. This is called diffraction. The spreading out of the waves is called diffraction, and diffraction is a clear sign that whatever is passing through that opening is in fact a wave. You can see the difference here. When we start to open up that opening and it's much larger than the wavelength, then you don't get that type of wave behavior. You don't get that diffraction or that spreading out. And instead you get what we know as a shadow, right? You get some light passing through, and then wherever the light doesn't come through, you have a shadow. And so when the openings, like these doorways, are much wider than the wavelength of the light that's coming through, you get your nice, crisp, clean shadows. Whether a wave spreads out by diffraction or you see the sharp shadows when the opening is large, it really depends on the size of the object in which the wave interacts with. So if we were to increase these wavelengths to be roughly the size of this opening, we would see diffraction occur. So the opening size must be around the same size as the wavelength of the wave in order to see diffraction, and thus the wave properties. So we're going to be, we're going to be talking about light, but light is a general term for any electromagnetic wave. You might think of light as what comes out of the sun or the colors, red through violet, but in fact, everything that we talk about can be applied to the full spectrum, the full electromagnetic spectrum. But we're going to just restrict our conversation to the visible spectrum simply because our eyes would not be able to see these effects occurring if we were to use any other kind of wavelength, right? Our eyes are only able to view and interpret visibility through this wavelength range. You might recall the speed of light is 3 times 10 to the 8 meters per second. And you can obviously use the fundamental wave equation to solve for the frequency or the wavelength of the light if the other quantity is known. We're going to talk about light as it passes through other materials such as water, glass, or air. And what happens is when the light waves pass through these other materials, they slow down. They go slower than the speed of light. We can calculate the speed of light in a different material by knowing the material's index of refraction, n. And the index of refraction, n, is defined by a ratio. It's the ratio of the speed of light in vacuum, which is 3 times 10 to the 8, divided by whatever the speed of light is in that particular material. And so because of this ratio, and because we know that light can never travel faster than 3 times 10 to the 8 meters per second, n will always be greater than 1, because v will always be less than c. Therefore, the index of refraction in vacuum is going to be 1. And the index of refraction of any other material will be some number greater than 1. Here's an example. So as we go from air to water to glass to diamond, you can see the index of refraction increasing. And what that means is that light is going to travel slower in these materials, slower and slower. What you need to know about light behavior when it goes into another material is you need to know that the frequency of the wave does not change. And that's because the frequency is determined by the source. The source of that light is going to dictate what the frequency is, and there's nothing that can change that. So, well, if the wave is going to slow down as it passes through another material, some factor in v equals lambda f must change, right? So if f stays the same, and we know that the speed goes down when it enters a new material, that means that the wavelength must go down. And so we can use the index of refraction to calculate the new wavelength of the light when it enters in a material with index of refraction n. And so the wavelength of the light in that particular material is going to be the wavelength of light in vacuum divided by n. And you can see here how that's determined through this relationship. Take some time to examine this relationship here, these relationships, to fully convince yourself of this. And so what you'll see then, right, if the velocity decreases when you enter in a new material, well, then the wavelength is going to get smaller. It's going to get shorter. So let's look at this quick check problem and apply that principle. So a light wave is traveling from air into glass. Which diagram shows the correct wave fronts? So recall that this distance between wave fronts is going to be the wavelength. And so since we're entering a material with a higher index of refraction, we're going to look for a wavelength to decrease in the glass. Obviously, it does not do that here. It's the same, so it does not do that here. And only in option C is where you see the wavelength get smaller than in air. Here's another example. Let's say we have orange light with a wavelength of 600 nanometers, and it's being shined upon a 1 millimeter thick glass microscope slide. The question is, what is the speed of light in the glass? And how many wavelengths of light are inside that slide? So we can use the index of refraction to determine the new speed. We saw that the index of refraction is a ratio between the speed of light in vacuum and then the speed of light in the wave. So we can use that to solve for the speed of light of the wave in that new material. It's simply the speed of light in vacuum divided by the index of refraction. Glass has an index of 1.5. And you can go back to the table to see that. So we're going to take 3 times 10 to the 8 divided by 1.5. And we get 2 times 10 to the 8 meters per second. So that's how fast the light is traveling in the glass. So now the question is, how many wavelengths of light are inside the slide? Well, if the slide is 1 millimeter thick, 1 millimeter is 0.001 meters. We want to know how many wavelengths exist in 0.001 meters. First, we need to determine what is the wavelength of the light inside the glass slide. We know it's not going to be equal to the wavelength in vacuum, right? This is the vacuum wavelength. So we need to find the wavelength in the glass, and that's going to be the vacuum wavelength divided by the index of refraction. (600 nanometers divided by 1.5). The new wavelength is 400 nanometers. So the question is, how many wavefronts can you fit in 1 millimeter, right? If each of these are 400 nanometers, how many of those, capital N, will fit in 1 millimeter? So we can figure that out by solving for N, right? I'm sorry, I'm writing all over the slide. N times 400 nanometers is going to give us the full length of the glass. And I realize my units are not matching, so let's change that to 400 times 10 to the 9 meters. And so we're just solving for N here. Let's see what that is. You get about 2,500 wavelengths within that glass slide. So the big thing that we're going to talk about in this lecture is what happens when light interferes with other waves of light. What we saw earlier is that waves can interfere with one another, and this interference is a wave-like phenomenon. For example, if we shine a laser light of some wavelength through a slit that has a comparable width to the wavelength, we're going to get that light spreading out. And what that spreading out is a result of is interference. We're going to use the double slit experiment, which is essentially what we just looked at in the previous slide, except now there's 2 slits. Each slit is going to act like an individual source of light. And so those 2 sources of light are going to interfere with one another. We're going to image that interference by placing a screen for the light to land on. And what you notice in the experiment is you're going to have regions of bright light and regions of no light. Those regions are a result of constructive or destructive interference of those 2 sources. You might recall that to determine the constructive or destructive interference conditions, you need to know the path length difference. And you're going to relate that to integer multiples of wavelength or integer multiples plus 1/2 of wavelength. So in this situation, the path length difference is going to be the difference between the source going through the first slit and the second source going through the second slit. So these distances R1 and R2, we're going to subtract them, and that's going to give us the path length difference. And then those path length differences are going to be related to the wavelength of the light that is going through the slits. You're also going to see destructive interference when we look at the absence of light, or the dark fringes, as we call them. Where there is no light ending up on the screen, you know that the path length difference between the two slits is going to be equal to some wavelength plus half a wavelength. So you can see that on the screen, you're going to have several regions of constructive interference and several regions of destructive interference. And that there's an alternating constructive destructive pattern. These are called the interference fringes, and they all oscillate around a central maximum that is 90 degrees from the slit. So this is the geometry that we're going to use in order to determine if we have constructive or destructive interference. So the geometry is centered around our slits and our screen being a distance L away from each other. And of course, the constructive interference condition is going to be the result of the path length difference between R1 and R2, which we'll call delta R. And that's going to be equal to an integer number of wavelengths. So the question is, can we use this geometry to determine what is delta R? We're going to zoom in right here and figure out how to express delta R with this geometry. So when we zoom in, let me erase all this and we'll bring it back. We must find positions on the screen where delta R is equal to m lambda, and you saw that there are multiple. So let's take an arbitrary one that is some distance y from y equals 0. And you'll notice that if we were to trace a line from the center of the two slits to y, we would be at an angle theta above that horizontal y equals 0 line. We can use that right triangle to find a relationship between the y position, which is the location of the constructive interference, and the angle theta and the distance L between the slits. So this is the right triangle that we're looking at right here. And so you can see that right triangle. What we know about it is we know the height of the right triangle, which is y. We also know the width of that right triangle, which is L. And angle theta is also known. And so in order to find y, we can express it in terms of a tangent, right? Which is opposite. Tangent theta is opposite over adjacent. And so our opposite is y and our adjacent is L. And so you can see we have an expression here that relates all three of those parameters. And so that is going to be kind of a secondary equation that can come in handy when solving these problems. We're still going to develop the first equation. Okay, we're going to work on what delta R is. But now you can see the second equation that you'll be using. So now let's zoom in and work on what delta R is. Delta R we can figure out by forming a second triangle. So you can see we're zooming in right here because we want to find the path length difference. And so if this is the path of one source of light and this is the path of the other source of light, this little distance right here is going to be the path length difference, right? This is how much longer R2 is than R1. And so we can form a triangle with that because we know this part of the triangle, right? This is D, the slit spacing. So we're going to create a right triangle, and this theta is going to be equal to this theta through some geometry. So you'll just have to take my word for it. We're not going to dive into that geometry, but just know that this theta here that we use to find tan is exactly the same as this theta right here. And so now we can use this triangle and we can write down our knowns and we can solve for delta R. So it's a little bit hard to see, but if this is the right angle here, then D is the hypotenuse of that triangle. And delta R is going to be the opposite side. So what trig function do you have when you use opposite over hypotenuse? You have sine, right? And so if sine theta is equal to opposite over hypotenuse, then that means it's equal to delta R, our path length difference, divided by D. So now we can rearrange to solve for delta R. And you can see that delta R will equal D sine theta. So now we'll insert that delta R into equation 1 up here. And what you see is that our bright fringes, our constructive interference, will occur when m lambda is equal to D sine theta. And so your theta is going to change depending on what fringe you're looking at. And so that's why fringe angle will have a subscript m. And that m is going to correspond to which order of fringe you are looking at. So now let's look at our fringes. Let's look at our bright fringes. So our bright fringes are going to occur in different locations, given by different angles theta. So our central maximum is our horizontal line. And then this m equals 3 fringe is going to be at some angle theta 3. Our m equals 2 fringe will be at some smaller angle, theta 2. And then our m equals 1 fringe will be at some smaller angle, theta 1. And so those 1, 2, and 3 are going to correspond to what order the fringe is. Here are the two equations that you'll be using to analyze the double slit interference. And so here's the first one, which has been rearranged to solve for sine theta. And this is going to be the location of the bright fringes. We're going to examine equation 2 and make some substitutions. So if you take a look at equation 1 up here, if the angles that we're dealing with are small, we can replace sine theta with theta. And to convince yourself of this, I want you to put your calculator in radian mode and type in sine of 0.001 and see what your answer is. What you're going to get is your answer is 0.001. And so just using your calculator, you can confirm the small angle approximation is valid. So with that, the left-hand side becomes theta, and the right-hand side is md over lambda. And the right-hand side is m lambda over d. So what we can do is we can also make a substitution for y over L. Since we know y over L is equal to tan theta, and tan theta is sine theta over cosine theta, which is going to be equal to theta over the small angle approximation, we can see that theta is also equal to y over L. So now we can replace the left-hand side of equation 1 with y over L. And then what has happened here is they moved L to the other side of the equation. And so these are the two equations you can use for double slit diffraction. From those, we can develop some additional equations, and one of them is the spacing in between bright fringes. The spacing in between bright fringes is going to be the distance between the two y values of the adjacent fringes. So in other words, the height between m equals 1 and m equals 0. That's going to be our delta y. And so if we plug in equation 2 in here and do some algebra, what you see is that the spacing between adjacent fringes is simply equal to the wavelength times the length between the screen and the slits and divided by the slit spacing. Let's talk about the dark fringes. The dark fringes are going to obey the destructive interference condition, which simply means that the path length difference is going to equal an integer plus 1/2 of a wavelength. We can use this relationship to determine the path length difference, where we made that small triangle, where this is D and delta R. That relationship holds regardless if we're looking at a dark fringe or a bright fringe. And so doing so, we can see that the path length difference equals D sine theta. Well, for destructive interference, we're no longer going to use m lambda, we're going to use m plus 1/2 lambda. And so we make that substitution, and we make also an additional substitution that we showed before, where we used the small angle approximation and substituted theta for y over L. And you can see that the dark fringes are a location y prime from the central max. From this, we can conclude that the dark fringes are located exactly halfway between the bright fringes. One thing to note about the double slit interference experiment is the brightness of the fringes. They start off very bright near the center and they become less bright towards the ends. This is because the light intensity from each slit is not uniform. So let's take a look at this example. So we have a double slit interference pattern observed on a screen. And so a picture of what we're dealing with is we have our screen over here and it's showing our bright fringes. Okay. And what we know is that the length between the screen and the slits is 1 meter. We know that the distance between the slits is 0.30 millimeters. And so what is it that they're asking us? If we know that from the center of one particular fringe to the center of the 9th fringe from this one is 1.6 centimeters, can we find the wavelength? So let's unpack this sentence. Okay, from the center of one particular fringe, so we don't know which one, so let's just pick a random one, maybe this one. All right, this is one particular fringe, m equals question mark, to the 9th one from that fringe. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, m equals question mark plus 9. Okay, that distance, which is blown up for scale, is a delta y of 1.6 centimeters. That's what we know. So how can we determine the wavelength of the light? Let's look at some equations that we were given to deal with this. We have our equation number 1, which relates the angle to the wavelength and the slit spacing through that little delta R triangle, right? Remember that? And then equation 2 was using the small angle approximation to relate the height of one fringe from to the wavelength. What we saw was we had y equals m lambda L over d. And we had a third equation, which was the spacing between adjacent slits, which is simply lambda L over d, right? That's a delta y between two adjacent slits, between m plus 1 and m. So if we look at equation 1, we don't know the angle, so we couldn't figure out lambda from there. And we also don't really know m, because we only know the relationship between those two slits. We don't know what actually, or what order those slits actually are. Number 2, we have something that looks like y, but we don't know that order m again. So we can't really use equation 2 either. That leaves us equation 3. So what does equation 3 relate? Equation 3 relates the spacing between adjacent fringes. And we know that the spacing is equal between any adjacent fringes. And so we can use that to our advantage, because what we know is we have 9 spacings to deal with, right? And so what we know is we know that 9 times delta y is equal to 1.6 centimeters, which means that on the right-hand side, 9 times lambda L over d is going to equal the 1.6 centimeters, right? Because if we multiply the left side by 9, we have to multiply the right side by 9. And so we can use this equation to find lambda, because we know L and we know D. So let's solve for lambda. Lambda is going to equal D times 1.6 centimeters divided by 9 times L. And so let's write everything in SI units. So 0.3 millimeters for D is 0.3 times 10 to the minus 3 meters. 1.6 centimeters is 1.6 times 10 to the minus 2 meters. And then L is 1 meter. So our wavelength, which we expect to be in the visible range, or else we wouldn't have been able to see the fringes at all, is going to be 533 nanometers. 533 times 10 to the minus 9, or if you're in your calculator, you probably got 5.3 times 10 to the minus 7, just 533 nanometers, which is in the visible light range. This is another example problem that you should do on your own to prepare for the exam. So let's talk about the diffraction grating. A diffraction grating is essentially a multi-slit device. So instead of 2 slits, you have a whole bunch. So we have multiple slits, and so therefore we're going to have more than 2 sources of light interfering with one another. We're going to use the exact same geometry to determine the slit spacing, the wavelength of the light, and solve problems like we were just doing. Our constructive interference condition is exactly the same. Our geometry of the problem is exactly the same. But qualitatively, what you notice is different about the multi-slit or the diffraction grating is that our bright fringes have become narrower. While the bright fringes have become narrower, the distance between them is exactly the same. We're going to be using all the same equations from the double slit and applying them to the diffraction grating because the geometry of the problem is exactly the same. It's just that now we have multiple slits, multiple sources of light that are interfering with each other. We have the exact same equation 1. Equation 2 looks a little different, and that's simply because we cannot use the small angle approximation for the diffraction grating. And so we don't approximate tan theta or sine theta as theta. We just leave it as the trig function. So qualitatively, like I mentioned before, if we look at the double slit, it's the location of the bright fringes are exactly the same as the multi-slit. It looks like they're spaced farther apart because they get narrower and narrower, but you can see the center line is in the exact same location regardless of how many slits you have in your diffraction grating. The other interesting result is that the fringes are much brighter. And that's because we simply have more waves interacting, the more slits you create. And so in this quick check problem, we're testing that exact concept. You notice that as the number of slits increase, what happens to all of the other parameters? What we know is that the brightness increases, so we definitely can rule out options A and B. We know that the positions stay the same and get brighter, and they get narrower, so that sounds good. The fringes stay the same but get dimmer, no. The fringes get brighter, narrower, and closer together, no. So C must be the choice. So let's do another example. This is an interesting type of diffraction grating. A feather has equally spaced openings between the barbules of each, of the feather. And so it can be used as a diffraction grating as a result. What we know is if the barbules are spaced at 50 per millimeter, what is the first order, m equals 1, diffraction angle, theta 1, for blue light and for red light? So what you may have noticed earlier is D, it has units of meters, right? That's the slit spacing, the spacing between the slits. What we were given here in this sentence is not D. What we were given is the spacing, which is 50 per 1 millimeter. So what we need to do is we need to turn that into D. And the way you do that is you simply invert this, right? Invert it to get D. And so let's do that. 1 millimeter per, 1 millimeter, and there's 50 barbules in between. That's what it's saying, that this is 1 millimeter and there's 50 barbules in between. And so therefore the spacing in between is roughly 1 millimeter divided by 50. So 1 millimeter is 1 times 10 to the negative 3 meters, and divide that by 50. We can get our spacing. It's slit spacing. Which is 20 times 10 to the minus 6 meters. And so now we just need to find the angles, the diffraction angle theta 1 for red light and for blue light. So we're going to use equation 1 to do that. And we'll plug in our wavelengths. So for blue light, lambda is 450 nanometers. So sine of angle theta 1 will be equal to 1 times 450 times 10 to the minus 9 divided by our slit spacing. And we'll have to do inverse sine to find that value. Make sure your calculator is in degree mode. .3 degrees for blue. Now let's do red. Our wavelength for red is 650 nanometers. We get 1.86 degrees for the angular location of the red bright fringe. And so I'm just going back to make sure that that's what they wanted. They didn't want the distance, they didn't want the difference in angle, right? So I think in your homework, it might want delta theta, which would be the, subtracting the two. But in this example, it only wants the two individual values, but just so that you are prepared for homework questions. So this is our actual result. This is the, solutions from when I did this in class. Same answers. Okay, good. So let's talk about an application of this, okay? The multi-slit diffraction is a very useful tool, and it is used a lot. It's used in spectroscopy, which is the science of measuring the wavelengths of atomic and molecular emissions, right? There's no way to measure the wavelength of light that comes from, let's say, a transition of, the carbon atom going, where the electron goes from one valence shell to another, right? We don't have a direct way of measuring the wavelength of that. What we can do, though, is we can create those emissions, funnel them through a diffraction grating, and see the slits that are created. And then we can measure either the distance between the slits, y, or we can measure the angle, right? Those are things that we can measure easily. we can turn those back into the wavelength and thus determine the wavelength of an emission. Here's an example. So let's say we have some kind of liquid where, you heat it up or you do something to the liquid and it causes the atoms and molecules in the liquid to create light through those atomic or molecular transitions. And so we're going to shine that light through the grating and we're going to see the location of multiple bright fringes, one for each wavelength of the light coming through. And so what we can do is we can measure the distance, ym. We could also, if we wanted, measure the angle, and from that, find the wavelengths. This is an example of doing just that. I skipped it in lecture. I'm going to skip it here. I don't have any exam questions planned for this particular application, but this could come up again in your future courses, depending on what your major is. So it might be worth looking at. Oh, and what I will say is this definitely will come up on MCAT, this application. It's very common to come up. So I would look at this and just put a bookmark in it and come back to it when it's time to study for the MCAT. So this is our summary or synthesis slide, and it shows you all the relevant equations for the double slit and for the diffraction gratings. And you'll notice the only difference between the two is the small angle approximation is used here to determine the distance between m equals 0 and the bright fringe m. Whereas in this diffraction grating, we don't use the small angle approximation. And then also we can determine the slit spacing by from the number of slits per millimeter, like we did in the previous example. So we're going to talk about another type of interference. And this one has some special rules to it, okay? This is called thin film interference. So we need to refer back to the previous chapter when we looked at what happened to the wave on a string when it reflected from a boundary. We saw that when we had a thick string attached to a thin string, when you shook that string, the wave, when it encountered that transition, some of it reflected and some of it continued to go through the thin string. So this is going to happen in thin film interference with light. Light is going to encounter a boundary, which is a change in index of refraction. Some of the light is going to go through and enter the glass or the plastic or whatever it is, and some of it's going to get reflected. This is used in anti-reflection coatings or on sunglasses, or even you can notice thin film interference when you see the iridescent colors on an oil slick or a soap bubble. And we're going to talk about that. So let's start from the beginning. We're going to describe what happens when light waves meet a boundary and the index of refraction changes. Part of the light is reflected, and then part of it is channeling or refracted through the glass. And this is evident here in this picture. You can see here there's a candle in front of a mirror, and the mirror is showing two reflections. Why is that? Well, maybe you didn't know this, but a mirror is actually a piece of glass. It's a piece of glass, a thin one, and on the back of that glass is a coating of aluminum. And so what's happening in this picture is you have light hitting the front of the mirror and turning around and coming back into our eye so we can see it. And then you have some of that light going through to the back end of that glass, and then that is coming out, and it looks like two images to us. In other words, two reflections. So let me show you a picture. We have an incident light wave entering a material of a new index of refraction. Part of that wave is going to be transmitted, and it's going to continue going on its merry way. What happens to the reflected part depends. One option is if the initial index of refraction is larger than the second, the reflected wave is going to be essentially the exact same wave coming back, right? Starts off at a minimum and goes up to a max. Starts off at a minimum and goes up to a max. So that's when N2 is less than N1. Or in other words, N1 is greater than N2. What about the opposite case? What if N2 is greater than N1? Then your wave, upon reflection, encounters or experiences a phase change. So you can see it starts off at a min and goes to a max here in case 1. In case 2, when index 2 is larger, you have starting off at a max and going to a min. And so you have a phase change, and what that phase change does is it adds an extra half a wavelength. And guess what? That's going to influence our constructive and destructive interference conditions, right? Because our constructive and destructive interference conditions depend on the path length difference. So let's take a look at those two waves interfering with one another, right? The first wave is the reflection from the top of the film, the air film boundary. The second wave that's going to interfere with that one is going to reflect off the film, the second boundary, which is between the film and whatever's to the right of the film, in this case, glass. So you can see that the two waves that are interfering with each other are a result of the reflection from the top and the reflection from the bottom of the film. Those are the two waves that are overlapping and interfering. And so that means that the path length difference is going to be related to the thickness T of the film. If the waves are in phase and they can interfere constructively, what we interpret that as physically is we have a strong reflection. So if you see a bright color upon reflection, that means that you had constructive interference occurring, and you can see that light. If the waves are out of phase, for whatever reason, they're interfering destructively, then we don't see that light. We don't see a reflection. We see nothing. We see an absence of light. So we need to take our constructive and destructive interference conditions and relate them to their path length difference, and also incorporate the fact that in one case you could not have a phase change, and in another case you could, right? Because that's going to change the path length difference. The way we do that is by adding the effective path length difference that comes from that half a wavelength phase change. So there's two situations that could possibly occur, and it depends on the index of refraction of each element in our film. If neither or both waves have a phase change, then the effective path length difference is simply 2 times the thickness. If only one of the waves, either the one that reflects from the top or the one that reflects from the bottom, has a phase change, then our path length difference is effectively increased by half of a wavelength. And if that's the case, then what happens for number 2, for case 2? Then that is going to make our constructive and destructive interference conditions change places. So here, this is our 2 formulae that we're going to be using, right? This you might recognize, path length difference, integer multiple. This is going to be constructive interference, right? But for the case of one reflective phase change, it's actually the destructive interference condition. And same for our what we normally recognize as a destructive interference condition for 0 or 2 phase changes is actually going to be the constructive interference condition for when there's 1 phase change occurring. And so the other aspect of these equations that I want to point your attention to is this guy right here. We're dividing by the index of refraction of the film. And so why is that? Because in the film, the wavelength changes, right? If we have a film and then here we have air and air, we have our wave entering the film, and as we saw, it's going to change its wavelength, right? The wavelength's going to shrink inside the film. And so since we're talking about the film thickness, we need to relate that to the wavelength of light in the film, which is taking the wavelength as given in the problem and dividing it by the film's index of refraction. We skipped this one in class, but let's talk about it. If we have a film of thickness T, and we know that it gives constructive interference for a wavelength in the film, lambda film, how much thicker would the film need to be in order to produce destructive interference? So we know constructive interference is occurring for 2T equals M lambda film, right? And I'm not including the N because we're dealing with lambda film, so the N has already been incorporated. And so in order to turn that into destructive interference, what would the thickness of the film need to be in relation to lambda? So for destructive interference, let's say that we're at M equals 1. Just picking a random M. That means twice the thickness of the film must be equal to the film's wavelength. In order to get destructive interference, we have twice the thickness of the film must equal M plus 1/2 lambda film. And if we're using our M equals 1, that means 2T must equal 3/2. 1 plus 1/2, 3/2 lambda film. Let's solve for T. Which is 3/4 lambda film. How much bigger is that than the original thickness? So let's do this. Let's call this T prime. This is the new thickness. Let's find the old thickness and compare to see how much larger it would need to be. So this is the original thickness, which is lambda film over 2. And so how much bigger is lambda film over 2 than 3/4 lambda film? It's bigger by 1/4, right? 3/4 is larger than 1/2 by 1/4, by 1/4. And so therefore, the film must be thicker by an amount equal to lambda film over 4. I think I used this picture to demonstrate what we need to do in order to determine if there is an inversion or a phase shift or not. So let's do that. Let's do that here again. So I picked some sample. This is not related to this example. This is just determining whether or not you need to use the constructive interference for 1 phase shift or for 0 or 2 phase shifts. So here I have 1, index of 1, index of 1.5, and index of 1.33. And so what I'm going to do is I'm going to sketch the light entering, bouncing off of the first boundary. And so that is reflection 1. And then that light that we initially sent in is going to hit this boundary, and it's going to reflect, and those are going to be the 2 wavelengths that are interfering with each other. And so what we need to do is we need to determine where is there a phase change occurring. So the phase change only occurs when the initial index of refraction is smaller than the second one. And you can also write it as N2 greater than N1, where the second one is bigger than the first, right? Those are equivalent statements. And so let's see where that happens. So I'll use blue. So we go from 1 to 1.5. We do have a phase shift here. So I'll mark that in blue. Yes, phase shift. Here, we're going from 1.5 to 1.3. No, we do not have a phase shift. And therefore, for 1 phase shift, our constructive and destructive interference conditions change. And so the constructive becomes 2t equals m plus 1/2 lambda over n. And then the destructive is actually 2t m lambda over n. So this is something that would definitely come up on the exam. You will need to know first, is there 0, 1, or 2 phase changes occurring? And if so, this is the proper condition that I need to use. This is explained in this tactics box, okay? This is kind of like your instructions for completing a problem related to thin film interference. So when you get a thin film interference problem in your homework or while you're studying and you're not sure what to do, follow these directions and you will get it and it will make sense. So let's put that to the test with this example. To keep unwanted light from reflecting from a surface of glasses or some other kind of lens, you put a thin film of material with index of refraction 1.38 onto the plastic lens. The question is, what is the thinnest film that will minimize reflection for this type of light? Lambda equals 550 nanometers. So let's draw a picture. So we have our thin film, and then we have our plastic, and then in front of it is air. So let's first check what phase changes occur. This says 1.38. So let's send in our first ray of light. It's going to bounce off that boundary and turn around. And the question is, this reflective wave, does it have a phase change or not? Yes, it does, because it goes from 1 to 1.38. So we have a yes phase change. I'll make purple as yes phase change. Well, that light we initially sent in is going to some of it's going to go through that film, and it's going to get reflected as well. And so when that one reflects, does that one have a phase change? Goes from 1.38 to 1.5, so yes, it does. So we have two phase changes occurring. So if two phase changes are occurring, we know that our constructive interference condition is going to stay the same, 2t equals m lambda over n. And we know our destructive is going to be 2t equals m plus 1/2 lambda over n. And so which condition do we need in order to solve this problem? We're looking for preventing reflection, minimizing reflection. So we're looking for destructive interference. So we're going to use the destructive interference condition. And what are we solving for? The thinnest possible film. Well, the thinnest possible film is going to be the film with m equals 0, right? Because when we solve for t, the way that we minimize that t, we can't change the wavelength, and we can't change the index of refraction of the film. So what we can reduce to be as small as possible is m. So we're going to use m equals 0, and we'll solve for t. And then divide by 2, so there's another 1/2 there. And so the thickness of the film, the minimum thickness, is going to be lambda over 4n. Lambda was 550 nanometers. And then the wavelength, the index of refraction of the actual film is 1.38. And so the thickness of the film, which is related to the wavelength in the film, which is why we divide by 1.38, is 99.6 nanometers. This is a very similar type question that would show up on the exam. Very similar. Put a star. This is an example of how we can see some biology behind the interference of reflected light rays. So in many cases, like the previous example, we can use thin films to reduce reflections, but you can also use them to enhance reflections. So you might have noticed in the eyes of a cat or a dog at night, you see like a glow, right? This glow is the reflection of light from a layer in the back of the eye. And that is called this, Latin for bright carpet. So what happens is light reflects back through the cells of the retina after entering this film, and it gives the animals a second chance to detect light, and therefore increases their night vision, their vision at night, right? It's kind of amplifying the low levels of light that are existing at night, and by creating this constructive interference that allows the light a second chance to go to the retina and be used to determine the position of objects. So this example illustrates that idea. And so what we need to do is we need to look for, instead of destructive interference condition, like we did in the previous example, we're looking for the constructive interference condition, because we want light to be reflected after at its maximum possible way. In other words, constructively interfere after encountering the film. So I'll let you do this example, but know that we are looking for the constructive interference condition. And so you'll need to determine what the phase changes are, if there are any, in order to know which constructive interference condition to use. So I'll let you do this one on your own. So let's talk about some other arrangements of thin films. So what we looked at is we looked at air, film, and then like a lens, right? So we had air and then the film and then some other index. Now we're going to shift our attention to situations where instead of on the back side of the film, you have, some high index of refraction material. What if it's simply just air again? Well, obviously what that's going to do is it's going to change the phase, the inversions of the wave, right? You're going to get a phase change at this boundary because you're going from 1 to 1.3, but here you're going from 1.3 to 1, you won't get a phase change at this boundary. So whenever you're dealing with thin films in air, you will be dealing with the situation of one phase change. And this is a time where we can talk about the difference in sources of color. So when you look at a bubble, you obviously see these beautiful colors, right? These colors are a result of constructive interference through a film of air bubble, a film of soap, which has air on both sides. Color also comes from pigment. So structural color is something like the colors from a bubble or the colors from the layers of pearl in a shell. And so when you see colors like this and they're iridescent, they are called structural color because they exist due to the material structure. If you were to zoom in on a small little piece of this shell, it would actually be clear or white or transparent. It wouldn't actually be that color. And so structural color comes from the fact that the object structure is creating thin film interference. Now you have pigmented items, and that is when color comes from a pigment, such as color in makeup, right? There's actual material added to makeup to change its color. The color is not a result of diffraction or interference. The way you can tell if something has structural color is if it's iridescent. If it's iridescent, that means that interference is creating the color due to the white light being reflected strongly in some wavelengths and missing in others. We are going to skip this quick check problem. The following conceptual example, I want you to read through them and have a good understanding of them. We're also going to forego section 17.6, circular aperture diffraction, which is essentially another type of diffraction. And we reach the end of the chapter where we have the summary, and these are great slides for you to study from. Multiple slit diffraction is what you need to look at. For the exam, don't worry about circular aperture. And then this is going to be your best friend, your thin film interference slide. And that's going to be the end of this lecture. Thanks for listening.